Hi, my name is Alan Tu, and I will present TransFIRA, a transfer learning method for explainable encoder-specific face image recognizability assessment. Our paper is an oral presentation at the 20th IEEE International Conference on Automatic Face and Gesture Recognition, or FG 2026. TransFIRA enables state-of-the-art template aggregation performance through principled filtering and recognizability-aware weighting, outperforming previous face image quality assessment methods. Additionally, we provide novel extensions to body recognizability prediction and encoder-grounded explainability. Our full manuscript and code are available at transfira.github.io. We will begin with some background on face image quality assessment and template-based biometric recognition. Conventional image quality assessment metrics are not reliable estimators of face recognition model performance. This is because visual cues like blur and exposure are not consistently aligned with the decision geometry of the encoder. Existing face image quality assessment, or FIQA methods, struggle in unconstrained real-world scenarios. In addition to being trained on generic face recognition datasets like WebFace and evaluated on saturated benchmarks like LFW, their curated labels do not correlate with the cosine similarity used for feature matching, and they are coupled to the decision geometry of specific backbones and training objectives. Some methods also rely on expensive generative priors or slow stochastic sampling that aren't feasible in real-time applications. An example of a domain where existing FIQA methods fail on is Briar Protocol 3.1, a proprietary video surveillance benchmark from the IARPA Briar program. It includes footage from platforms like long-range security cameras and UAVs. Thus, Briar encoders are trained to handle challenges like extreme distances and angles, motion blur, atmospheric interference, and low light that are out of distribution for general face recognition datasets and open-source pre-trained encoders. In biometric recognition, a template is a comparable representation of a subject extracted from media. Template-based recognition is used in unconstrained face recognition. Two benchmarks are Briar Protocol 3.1 and IJBC, which consists of diverse web and video imagery. In template-based recognition, the gallery is a collection of templates for known subjects to be searched against. Each known gallery image and video frame is encoded as a feature, and the gallery center is a mean feature of all gallery features for a subject. A probe is input media containing an unidentified subject to be compared against a gallery for potential matches. A probe template is typically computed as a mean feature of the encoded probe images or video frames. In face image quality assessment literature, the corresponding face image quality score for each probe feature is used to calculate a weighted mean instead. The resulting probe template is then compared to the gallery centers using cosine similarity and matched to the closest class. Now, we will introduce our TransFIRA method. TransFIRA defines recognizability as the likelihood that an image will be correctly identified by a given encoder. This is different from image quality, which is not necessarily aligned with the given encoder's decision geometry. TransFIRA aims to determine how best to predict and utilize face image recognizability. We break this into three sub-questions. The first one is how to measure recognizability in an explainable way. TransFIRA defines three explainable image recognizability labels defined in the embedding space of the encoder. Given an encoder, probe image, and its embedding, class center angular similarity, or CCAS, measures how closely an embedding aligns with the gallery center of its own class. It is computed as a cosine similarity of the feature to its correct gallery center, mirroring how probe and gallery templates are matched. The nearest non-matched class center angular similarity, or NNCCS, measures the similarity of the feature to the gallery center of the most confusable imposter class. This is defined as a cosine similarity to the closest incorrect gallery center. The class center angular separation, or CCAS, subtracts NNCCS from CCS. This captures if the encoder predicted the correct class in the gallery and by what margin to the nearest incorrect class it made its decision. The second sub-question TransFIRA addresses is how to predict recognizability for a specific encoder. Given a pre-trained encoder, we predict and aggregate the gallery centers, then compute CCS and CCAS for each probe image in the training dataset. Next, we append a linear layer to the pre-trained encoder to regress ground truth CCS and CCAS. Finally, we fine-tuned this entire recognizability prediction network using mean-squared error loss. This transfer learning approach adapts the encoder to predict recognizability from its own embedding geometry, taking advantage of its pre-training and converging very quickly. Note that there are now two networks. The original face recognition encoder is untouched, preserving its original face recognition performance. Its separate recognizability prediction network is grounded in the face encoder's decision geometry. Since the recognizability prediction network has the same architecture and uses the same data loader as an encoder, it maximizes component reuse and can be easily dropped into a system's feature prediction and template aggregation pipeline. Furthermore, it does not rely on strategies like expensive generative priors or slow stochastic sampling that aren't feasible in many real-world deployment scenarios. The third question that TransFIRA answers is how to use predicted recognizability to improve template aggregation in a principled manner. In TransFIRA, a sample is recognizable if it lies closest to its own class center. CCAS directly captures this because it calculates the difference between the cosine similarity of the correct class against the cosine similarity of the closest incorrect class. If CCAS is greater than 0, then the encoder chose a correct class. If CCAS is less than or equal to 0, then the encoder chose an incorrect class. In other words, CCAS equals 0 can be interpreted as a principled threshold for recognizability. Our principled filtering method uses CCAS to exclude all images whose predicted CCAS is less than 0, ensuring that only frames that are confidently recognized by an encoder contribute to the template. Prior FIQA literature does not introduce any filtering mechanisms, and this is a first principled threshold grounded in the decision geometry of the encoder. In template-based recognition, cosine similarity is used for feature matching. CCS is defined as a cosine similarity of the sample with the correct class. Thus, the greater CCS is, the more confident the encoder is in the correct class, and vice versa. Our recognizability-aware weighting method computes a weighted average of the remaining features using their predicted CCS scores. Images that the recognizability prediction network predicts are close to the correct gallery center are upweighted, while those that are predicted to be far from the correct gallery center are downweighted. This emphasizes compact, reliable samples that are most representative of the correct class. Now, we will evaluate TransFIRA on the template and per image levels. There are two face recognition encoders in our evaluation setup. STR-JHU CoastFace, which was developed by STR and Johns Hopkins University for the IARPA Breyer program, is pre-trained on the proprietary Breyer video surveillance training dataset. InsightFace ArcFace is an open source, off-the-shelf encoder pre-trained on the open source WebFace 12 million dataset. We evaluate on two template-based face recognition benchmarks. Breyer Protocols 3.1 consists of proprietary video surveillance footage, while IJBC consists of diverse web and video imagery. For Breyer Protocols 3.1, the recognizability prediction networks are fine-tuned on the Breyer training dataset. For IJBC, they are fine-tuned on WebFace 12 million. As shown by these ROC curves, TransFIRA achieves state-of-the-art template aggregation performance on Breyer Protocols 3.1 and IJBC. When used separately, principled filtering and recognizability-aware weighting each outperform all previous FIQA methods on Breyer Protocols 3.1 by a wide margin. Combining them into our full TransFIRA template aggregation strategy provides an even larger boost. We also claim the highest results was the STR-JHU CoastFace encoder on IJBC. Notably, the verification performance of the open-source InsightFace ArcFace encoder on Breyer Protocols 3.1 improves from 0.43 to 0.87 TAR at 10 to the negative 3 FMR, and from 0.08 to 0.60 TAR at 10 to the negative 6 FMR, even though the ArcFace encoder itself was never pre-trained on any Breyer or video surveillance data. To our knowledge, these are the largest FIQA-driven gains yet reported in the literature, demonstrating the strengths of TransFIRA's encoder-specific and domain-specific approach. Furthermore, TransFIRA and CRFIQA have almost identical performance with the InsightFace ArcFace encoder on IJBC. This is likely due to training alignment, since all of these are trained on WebFace 12 million. This supports our argument that FIQA methods aligned with the encoder's training distribution and decision geometry achieve the strongest results. TransFIRA also achieves state-of-the-art image-level FIQA results for Breyer Protocols 3.1 and IJBC. On Breyer Protocol 3.1, TransFIRA's FNMR ERC results are the strongest by a wide margin. On IGBC, TransFIRA also yields the strongest FNMR ERC area under curve scores, being matched only by EDIF FIQA within 0.0001 at some operating points. Additionally, TransFIRA produces the strongest Spearman correlation with cosine similarity to the correct class because its predictions are directly grounded in the encoder's decision geometry. We also extend TransFIRA to 2 additional applications. In addition to face recognition, Breyer Protocol 3.1 also evaluates body recognition. There is no previous body image quality assessment literature. The SEM-ReID body recognition encoder developed by the STR and JHU team for the IARPA Breyer program produces CCS and NNCCS distributions that are tightly centered at 0.97. We sigmoid calibrate the label distribution by mapping NNCCS and CCS to 0 and 1, producing a training distribution that can be fit more easily by the recognizability prediction network. To our knowledge, this application of sigmoid calibration is novel in the context of FIQA and body recognition. We use the sigmoid calibrated distribution to extend TransFIRA to body recognizability prediction, improving template aggregation results on Breyer Protocol 3.1. These findings extend recognizability prediction beyond faces for the first time, establishing TransFIRA as a unified framework for modeling recognizability across modalities. Finally, TransFIRA provides an encoder-specific explainability signal for FIQA. We illustrate this property in our paper's appendix by exploring the effects of varying levels of Gaussian blur on CCS and CCAS. A deployment capability of TransFIRA is that it also extends to unseen subjects, including those with only a single enrollment image, where ground truth CCS and CCAS cannot be calculated. In such cases, predicted recognizability is the only practical way to assess whether a subject is reliably identifiable by the encoder, providing avenues for safeguards, re-enrollment, and hard example mining. TransFIRA was created by Alan Tu, a PhD student at the University of Maryland during his internship at Systems and Technology Research, or STR, in collaboration with Johns Hopkins University. This research was funded by the IARPA Biometric Recognition and Identification at Altitude and Range, or Breyer program, which focused on real-time multimodal fusion of incomplete face, body, and gait information for biometric recognition in severe operational conditions. In practice, TransFIRA's recognizability prediction methods are used to filter face and body detections and aggregate probe templates in the STR Breyer system. In conclusion, we introduced TransFIRA, Transfer Learning for Face Image Recognizability Assessment. Our paper is an oral presentation at the 20th IEEE International Conference on Automatic Face and Gesture Recognition, or FG 2026. TransFIRA enables state-of-the-art template aggregation performance through principled filtering and recognizability-aware weighting, outperforming previous face image quality assessment methods. Additionally, we provide novel extensions to body recognizability prediction and encoder-grounded explainability. Our full manuscript and code are available at transfira.github.io. Thank you.